Lifespan, Why We Age and Why We Don't Have to, by David A. Sinclair, Ph.D. Let me tell you about someone extraordinary. Her name was Vera. Picture this: a young woman growing up in Hungary during an era of poetry and art, spending lazy summers diving into crystal-clear lakes. But then history came knocking, hard. The Nazis arrived and commandeered her family's hotel, transforming it into an SS headquarters. Fast forward a decade, and there she was under Soviet occupation, boldly writing and distributing anti-communist leaflets on the streets of Budapest. When the revolution crumbled, she grabbed her young son and fled to the most distant corner of the world she could imagine, Australia. And she never once looked back. Vera became one of the first women brave enough to wear a bikini on Sydney's iconic Bondi Beach, and yes, she got chased off by scandalized authorities. She even spent years living solo in the wild, untamed jungles of New Guinea. Fearless doesn't even begin to describe her. She was so full of life that she refused to let her grandsons call her grandmother. To everyone, she was just Vera. She taught those boys to see the world with childlike wonder. Her mantra was simple: don't grow up, never grow up. And for decades, she lived that philosophy beautifully. Well into her 70s, she lit up every room she entered, spinning stories, laughing until dawn, an unstoppable force of nature. But then, something shifted. By her mid-80s, that vibrant spark had flickered out. She became fragile, ill, barely a shadow of her former self. The music that once made her dance became just noise. She told her grandson one day, almost matter-of-factly, "This is just the way it goes." She passed away at 92, having lived what most would call a full, rich life. But her grandson, David Sinclair, couldn't shake one haunting realization. The real Vera, the essence of who she truly was, had vanished years before her body gave out. What happened to Vera happens to every single one of us, and to everyone we hold dear. We call it aging. We call it inevitable. We shrug and say, well, that's just life. But what if we're wrong? What if aging isn't some immutable law of nature, but actually a disease? And what if that disease could be treated, maybe even cured? This radical idea forms the beating heart of Lifespan, written by that little boy Vera taught to stay young, Dr. David Sinclair, now a tenured professor of genetics at Harvard Medical School. This isn't some feel-good book about tacking on a few extra years at the end. It's a roadmap to a future where we don't just live longer, we stay younger longer. By the time we're done today, you'll understand why everything you thought you knew about aging is completely backwards. And you'll discover practical, actionable steps you can start taking today to literally rewrite your biological destiny. This isn't some far-fetched fantasy. This is cutting-edge science, happening right now, in labs around the world. And honestly, it's going to change everything. Let's wrestle with a question that feels almost too enormous. Why do we actually get old? For centuries, we've just accepted it as fact. Gray hair appears, skin wrinkles, bodies weaken. Diseases show up, heart disease, cancer, dementia, and we treat them as individual enemies to defeat. Our entire medical system basically plays whack-a-mole. A disease pops up, we throw billions at knocking it down. And we've gotten surprisingly good at it. But Dr. Sinclair points out a massive flaw in this strategy. If we completely eliminated cancer, every single type, it would only add roughly 2.1 years to average human lifespan. Cure all heart disease? Just 1.5 years more. Why so little? Because there's always another disease lurking in the wings. We're not addressing the root cause, only managing symptoms. The real culprit, the ultimate risk factor for everything else, is aging itself. So what actually causes aging? Scientists have proposed various theories over the years. Maybe our DNA deteriorates over time, like a document photocopied endlessly until it's unreadable. That's the DNA damage theory. Or perhaps it's free radicals, rogue molecules bouncing around inside cells, wreaking havoc. But Sinclair highlights a simple, profound mystery that demolishes these theories: cloning. Remember Dolly the sheep, the first cloned mammal? She came from a cell taken from a 6-year-old adult sheep. If that adult cell's DNA was fundamentally corrupted by age, Dolly should have been born old, right? But she wasn't. She arrived as a perfectly healthy young lamb. Since then, scientists have cloned numerous animals from adult cells, and they consistently live normal, healthy lifespans. This discovery is absolutely mind-blowing. It proves that even in an aged body, the fundamental genetic blueprint for creating a young, vibrant organism remains perfectly intact. So if the information itself isn't damaged, what's going wrong? This is where Dr. Sinclair introduces his revolutionary concept, the information theory of aging. He asks us to imagine our body's information existing in two forms. First, there's digital information. That's your genome, your DNA. It's incredibly robust, written in just 4 letters: A, T, C, and G. Like data burned onto a DVD, it's remarkably stable and can be copied with near-perfect precision for millennia. This is your blueprint, your instruction manual. Then there's analog information, the epigenome. If the genome is your computer's hardware, the epigenome is the software. It doesn't alter the DNA code itself, but it controls which parts of that code each cell actually reads. This is what makes a skin cell distinct from a brain cell, despite having identical DNA. The epigenome achieves this by physically packaging DNA, wrapping some genes tightly to silence them, while leaving others accessible to be read. Think about the difference between digital and analog music. A digital music file sounds identical every time you play it, but an analog cassette tape? Over time, it warps, stretches, and degrades from magnetic interference. It accumulates noise. The music becomes distorted, unrecognizable. The information theory of aging proposes that aging is essentially the loss of this analog, epigenetic information. Our cells gradually forget how to read the original blueprint correctly. Sinclair offers 2 brilliant analogies to explain this. First, imagine a DVD. The digital data sits in tiny pits on the disk's surface. But over time, the disk gets scratched. The data is still there, perfectly intact, but the DVD player's laser can't read it properly anymore. The movie skips and freezes. Aging, Sinclair argues, is the accumulation of these scratches on our epigenome. The digital DNA code remains fine, but the cellular machinery can no longer interpret it correctly. Or picture the genome as a grand piano. The keys are genes. The sheet music is DNA. But the pianist? That's the epigenome. When we're young, we have a master pianist who plays life's symphony flawlessly. But as time passes, the pianist becomes distracted, slightly confused. She starts hitting wrong notes here and there. At first, you barely notice. But gradually, the mistakes multiply until that beautiful concerto descends into complete chaos. The piano itself remains perfectly tuned. The sheet music is still correct. But the reader of that music is failing. This cellular confusion, this mounting epigenetic noise, that's what we experience as aging. So what's distracting the pianist? What's scratching the DVD? The answer, Sinclair discovered, lies in an ancient biological program that's been with us since life began. He calls it the survival circuit. Let's rewind 4 billion years to a shallow primordial pond. Life is just emerging. tiny, fragile cells struggling to exist. It's a brutal world of scarce resources and harsh conditions. In this survival of the fittest environment, one organism evolves a remarkable advantage. Let's call it Magna Superstes, the great survivor. It possesses a simple but ingenious two-gene circuit. Gene A stops the cell from reproducing. Gene B silences gene A, so when conditions are favorable, the cell can make copies of itself. But gene B has another critical function. It also repairs broken DNA. Now imagine cosmic radiation bombards the pond, shattering the DNA of countless cells. Most cells, driven by the fundamental urge to reproduce, just keep dividing. But their broken DNA gets scrambled, and they die. Not our great survivor. When its DNA breaks, the protein made by gene B abandons its post at gene A and rushes to make repairs. Because it has left, gene A is no longer silenced. It switches on, and the cell stops everything, halting division and hunkering down, channeling all energy into survival and repair. This is life's fundamental trade-off: reproduction versus repair. When times are good, you grow. When you're under threat, you defend and fix. This simple survival circuit proved so successful that it's been passed down through billions of years of evolution. It exists in every plant, every fungus, and every animal on Earth, including us. Our modern version of this survival circuit runs on a family of genes called sirtuins. Think of sirtuins as your cell's emergency response team. They're the guardians of the epigenome, the conductors of the cellular orchestra. Their primary job is traveling around the genome, keeping genes silenced that should be silenced, maintaining cellular identity, ensuring the pianist plays the right notes. But, just like their ancient ancestor gene B, they also have that second job, DNA repair. And here's where the problem emerges. Life is chaotic. Our DNA constantly breaks. Every single day, trillions of breaks occur in our bodies just from normal processes, not to mention damage from UV radiation, X-rays, or chemicals in our environment and food. Each time a break happens, sirtuins get pulled away from their regular posts. They rush to the damage site to coordinate repairs. When we're young, this system works beautifully. Sirtuins respond to emergencies, fix the problem, and return to their original posts. The pianist might miss a beat, but quickly recovers her place. But as we age and breaks become increasingly frequent, sirtuins are constantly being summoned away. It's like emergency crews in a city facing simultaneous fires, floods, and earthquakes. The crews become so overwhelmed, rushing from one disaster to the next, that they start forgetting where home actually is. They don't always return to the genes they were supposed to be regulating. Some genes that should be off switch on. Some that should be on switch off. This creates epigenetic noise. This scratches the DVD. This distracts the pianist. Cells begin losing their identity. They become dysfunctional. And this, Sinclair argues, is the singular reason we age. All the hallmarks of aging, mitochondrial decay, senescent, zombie, cells, telomere shortening, they're all downstream consequences of this fundamental loss of information. It's a compelling theory, but where's the proof? This led Dr. Sinclair's Harvard lab to conduct an extraordinary experiment. They created what they call ice mice, inducible changes to the epigenome. Using a gene from slime mold, they engineered mice where they could activate an enzyme that would cut DNA at specific, harmless locations in the genome. The cell's natural repair machinery would immediately stitch the DNA back together, leaving no mutations. They weren't damaging the digital code. They were just creating temporary breaks, the noise. that would force sirtuins to become distracted. What happened next was remarkable. The mice seemed perfectly fine during treatment, but several months later a postdoc called Sinclair in a panic. "One of the mice is really sick," she said. "I think we need to euthanize it." Sinclair asked for a photo. When it appeared on his phone, he actually laughed. "That's not a sick mouse," he replied. "That's an old mouse." At just 16 months old, relatively young for a mouse, the ice mouse displayed all the hallmarks of advanced age: thinning, graying fur, a bent spine, cloudy eyes, and paper-thin ears. Its littermates, who hadn't received the treatment, remained young and healthy. When they measured the mouse's biological age using an epigenetic clock, it was 50% older than its siblings. This was the smoking gun. They had accelerated aging without creating a single mutation. They'd done it purely by creating epigenetic noise. As Sinclair writes, "We hadn't given the mice all of those ailments. We had given them aging. And if you can give something, you can take it away." This is where the story pivots from fascinating problem to incredibly hopeful solution. If aging results from our survival circuits becoming overworked, and our epigenome getting noisy, then the key to staying young is activating those same circuits in a controlled way, without causing actual damage. This concept is called hormesis. What doesn't kill you makes you stronger. By introducing mild, beneficial stress, we can activate sirtuins and other longevity genes, boosting cellular defenses and quieting epigenetic noise. Dr. Sinclair outlines several practical ways we can do this right now. First, eat less often. Calorie restriction has extended lifespan for nearly a century in almost every organism tested, from yeast to mice to monkeys. But who wants constant hunger? Good news. You don't have to suffer. Intermittent fasting, skipping a meal or two daily, or restricting eating to a specific time window appears to provide many of the same benefits. When your body senses nutrient scarcity, it triggers the survival circuit. It's a powerful signal to hunker down and repair. Second, high-intensity interval training. All exercise helps, but short bursts of intense activity are particularly effective at inducing hormesis. This kind of stress signals your body to build stronger mitochondria, grow new blood vessels, and activate longevity genes. Exercise, at the cellular level, literally switches on genes that make us young again. Third, get uncomfortably hot and cold. Exposing your body to temperature extremes is another way to trigger the survival circuit. This explains why saunas and cold plunges are so beneficial. They activate protective brown fat and boost mitochondrial function. These are powerful tools available to everyone, but what about the next level? This brings us to molecules that can mimic hormesis effects. Sinclair's lab became famous for research on resveratrol, a compound found in red grape skins. Stress plants produce these molecules for protection, and when we consume them, they seem to trigger our own survival circuits. While resveratrol itself may not be a miracle cure, it provided crucial proof of concept. A single molecule could activate sirtuins and extend lifespan in the lab. More promising today are molecules that boost levels of a critical chemical called NAD, nicotinamide adenine dinucleotide. NAD is fuel for sirtuins. Without it, they can't function. The problem? As we age, NAD levels plummet. By age 50, you have roughly half the NAD you had in your 20s. This has sparked a race to find NAD-boosting molecules. Two of the most studied are NMN nicotinamide mononucleotide and NR nicotinamide riboside. In mice, adding NMN to their drinking water has produced stunning results. Old mice on NMN could run almost twice as far as untreated counterparts, so far, actually, that they broke the lab's treadmill. They showed better blood flow, stronger muscles, and reversed many aging indicators. The personal stories are equally compelling. Sinclair shares that his own father, in his late 70s, was beginning to show typical signs of decline. After starting NMN, his energy returned dramatically. Today at 80, he's hiking mountains, whitewater rafting, and has even launched a new career. He's living with the vitality of someone decades younger. But all of this, diet, exercise, even NAD boosters, is about slowing the scratches on the DVD. What if we could actually polish the disc and restore it to its original, pristine condition? This is the final, most mind-bending part of the book, Age Reversal. We already know it's possible. Cloning proves the youthful information still exists. The question is, how do we access it without creating an entirely new clone? In 2006, Japanese scientist Shinya Yamanaka made a Nobel Prize-winning discovery. He identified just 4 genes that, when activated in an adult cell, could erase its epigenetic identity and transform it back into a pluripotent stem cell, the kind found in embryos, capable of becoming any cell type in the body. These are called the Yamanaka factors. They're the biological reset button. The problem? If you activate them too long in a living animal, you can completely erase cellular identity, causing tumors. But what if you could turn them on just briefly? Could you reset the epigenetic clock without pushing cells all the way back to zero? This is exactly what Sinclair's lab has now accomplished. Using a safe virus, they delivered 3 of the 4 Yamanaka factors into old mice, and they decided to test it on one of biology's hardest problems, regenerating nerve cells. They took old mice that had lost vision due to age and mice whose optic nerves they had crushed, an injury that, like spinal cord damage, is considered irreversible. Then they activated the reprogramming genes. The results were breathtaking. The damaged optic nerves grew back, and the old, blind mice, their vision was restored. Think about the implications. They didn't just slow aging, they reversed it. They polished the scratches off the DVD, and cells could read the youthful information again. They reminded the confused pianist how to play the music. This isn't some distant fantasy. This is happening in laboratories today. The future Sinclair envisions is one where, every decade or so, we might receive a reboot, a therapy that resets our epigenome, clears accumulated damage, and restores our bodies to a younger biological state. A world where 90 is the new 50. A world where you have the energy and health to start a new career, master a new skill, or play with your great-great-grandchildren. Of course, this raises enormous questions. What about overpopulation? What about inequality? Will only the wealthy access longer lives? Sinclair tackles these challenges directly. He argues that historically, whenever human health and longevity improve, birth rates decline. A healthier, longer-living population is also more innovative and productive, capable of solving the very problems it creates. The goal, he insists, must be making these therapies as affordable and accessible as antibiotics or vaccines. The journey Sinclair takes us on in Lifespan is nothing short of extraordinary. It begins with a simple, heartbreaking observation about his grandmother and ends with a vision for humanity's future that is both audacious and, as he demonstrates, increasingly within reach. He dismantles one of our deepest beliefs, that aging is inevitable, and replaces it with an empowering truth. Our longevity is far more within our control than we ever imagined possible. After finishing a book like Lifespan, it's impossible to see the world the same way. The idea that aging is a disease, and a treatable one, feels so profound that it's like being let in on one of humanity's best-kept secrets. For me, the most powerful takeaway isn't just the science, as incredible as that is. It's the perspective shift. We're so conditioned to expect decline. We're taught to accept that our bodies will fail, our minds will fade, and our world will shrink. Dr. Sinclair offers a radically different narrative. It's a story of vitality, resilience, and potential. This isn't about desperately cheating death or clinging to life in a frail state. It's about extending health span, the years spent in robust health, free from disease and full of energy. It's about ensuring that who we truly are, our essential self, doesn't vanish years before our body does. The beauty of this book is that it doesn't just paint a distant future. It gives us a path forward, starting today. The principles of hormesis, eating less frequently, exercising more intensely, and embracing discomfort, aren't complicated or expensive. They're simple ways to communicate with our ancient survival circuits, gently nudging our bodies back toward youthful resilience. If I could suggest a few simple actions you could take right now, inspired by this book, they'd be these. First, try skipping one meal tomorrow, just one. Notice how it feels to let your body experience brief scarcity. You're activating ancient pathways that have been dormant far too long. Second, find a way to get breathless for 10 minutes. It doesn't require a full workout. Run upstairs, do a few sets of push-ups, or take a brisk uphill walk. That mild stress sends a powerful signal to your longevity genes. And third, next time you shower, end with 30 seconds of cold water. It's uncomfortable, sure, but that shock is another way to awaken those dormant survival circuits. These small actions are the first steps on Sinclair's path. They're ways of starting a conversation with your own biology, reminding it of the strength and resilience coded into your very being. That was a summary of Lifespan, Why We Age, and Why We Don't Have to, by David A. Sinclair. We've explored the monumental ideas today, but I'll be honest, a summary can only be a map. The real treasure comes from making the journey yourself. The true power of this book lies in those quiet reading moments, when a particular story resonates with your own life, or a scientific concept suddenly clicks and illuminates your world in an entirely new way. This summary is your guidepost, helping you decide if this journey is one you want to take. If anything we've explored today sparked something in you, I urge you to grab a copy. Reading it isn't just about absorbing information. It's an experience that could fundamentally change how you approach every single day you have left. Also, if this journey through Lifespan has given you a fresh perspective, please take a moment to hit that like button and subscribe to the channel. It lets me know we're on the right track and ensures you won't miss our next exploration into another transformative book. Let's keep discovering these powerful ideas together.